The middle of a project is simultaneously my favorite and least favorite place to be. On one hand, your tasks are clear. Just get the project done. The big picture isn't important here. On the other hand, the big picture can be a fun thing to consider. That's when you get to dream about whatever big thing comes next in your grand plan. This trade-off between decision-making and brainstorming is one of the peculiar things about being an engineer. I feel like I can't do both simultaneously, but I have to do both anyway. I feel like I have to flip a switch in my mind every time I switch from one to the other. Now, at the end of the last video and at the start of this video, that's where I find myself, in the middle of a project with a half-completed prototype of a miniaturized wrist-mounted material ejection device. Only once it's done can I truly consider how the technology can improve. That's just how I roll. So we've got a few design tasks to complete for today. First, we've got to figure out how this thing is going to latch. Before, I used magnets to create a bistable hinge and added some mechanical tabs. I wasn't super satisfied with this, so I'm going to see what else I can figure out. Second, we've got to design some small covers for all of the currently exposed electronics. Third, we've got to add some mechanical features for the battery so it's not purely held on by the electrical connections. That's a bad idea, which can quickly go wrong. Now, our goal by the end of this video is a fully functioning device, so we can get back to dreaming about what's next. I'm Will, and if you're like me, you grew up fascinated by the amazing fiction and biology-inspired inventions that spread around the internet in the aughts and 2010s. But I noticed something. For all the amazing academic and online work done in this area, these inventions have yet to impact our daily lives. That's where I come in. I have a PhD in mechanical engineering and a decade of research experience in electronics, design, materials, and artificial intelligence. Most importantly, I dream of bridging this gap. With a focus on user-friendly and inexpensive devices, I aim to democratize superpowers for the individual, enhancing our society through rescue robotics and self-defense devices from the wildest corners of our imagination. This fully functional device would not be possible without this video's sponsor, PCBWay. If you're in need of prototype fabrication, whether it's CNC machining, 3D printing, or printed circuit board manufacturing, PCBWay is your one-stop shop. Two of the innovations they made for me that power the work that you're going to see in this video are a super sleek pressure vessel that they machined and polished for me, as well as my custom microcontroller unit that has integrated motor control that they fabricated for me. Both of these innovations have advanced my progress greatly. I mean, just check out what I was making just 2 or 3 years ago versus what I'm making now. So check the link in the description for $5 off PCBWay's amazing services. And during the rest of the video, keep an eye out for the stuff that they made for me. So my last video did pretty well, and that means I can do one of my favorite things, which is to go through the comments. Mainly, I find it really encouraging that people seem to be really into the math parts of my videos. This, combined with the last video that did really well, tells me I got a lot of really cool, smart people in my audience. Reject brain rot. Accept calc.
If anyone joined the stream recently, calc stands for calculator. I'm just using slang.
There is hope for this generation. Also, I really appreciated this comment from Daisy Jones that highlighted the fact that I actually made this thing smaller instead of just shoving key components of it into a backpack. I agree that that sort of thing never really satisfied me. It always seemed like cheating. However, I have in the past been a card-carrying member of the Backpack Club. It definitely feels like more of an accomplishment to have a self-contained device, and that's something that I've been pushing for years now. Thus, I've got 2 signals from my audience. Math good, and my method of miniaturization good. I'm not sure how much math I'll be able to do in this video, but since we're gonna have to miniaturize anyway, it's good to know you guys are satisfied with my technique so far. Let's keep going with the latch of this bracelet. I had someone suggest a fun idea, or something similar. Since I have the female USB-C port at the end of this bracelet anyway, I could add a male USB-C port to the other end, and then they could connect together as the latch. As brilliant as this kind of is, and while it would definitely work in the short term, I don't know how I feel about using these electrical components for mechanical purposes. The way this connector is attached to the circuit board is definitely not meant to withstand a significant amount of force in any direction. I always had the idea to latch these 2 ends together in some way, but some great comments I got led me to realize I could choose between that and a latch located at the hinge. This would basically be something that stops the hinge from rotating when closed, even though the two ends remain unattached. There may be some problems with this, such as backlash and amplified force on the mechanism. So how can I more accurately compare the strategy of end latching and the strategy of hinge latching? I can make a chart and compare the expected score of each. I can calculate the expected score of these strategies by adding up the scores of various potential outcomes weighed by the probability of those outcomes. Here, to keep things simple, I'm just focused on negative outcomes, so their scores will be negative. The outcomes I'm considering here are the latch breaks, the latch is too easy to force open, the latch is difficult to align, the unlatch button is difficult to reach, the latch is difficult to design, the latch is difficult to repair, the design adds a significant amount of parts to the assembly, the design interferes with the established structure of the existing parts, and the latch is too difficult to close. This approach has some downsides, especially since I'm just one person. Typically, you want a whole group of people whose opinions are considered perfectly equal. But I'm just one person, so when I do this, I have to try to generate diverse opinions in my own head. I'm also trying to eliminate all my biases when constructing this chart, so it's entirely possible the scores end up to be very, very similar, even though I have no idea consciously of what the score is going to be before the calculation is complete. Also, the scores and probabilities here are completely made up. I have no idea what the probability of these outcomes are going to be. There is the advantage of forcing me to just look at each individual outcome instead of just giving each method a score outright, but my subconscious bias of giving these two an equal score could take effect. All right, so it's time to see the expected scores. Okay, 128. Son of a... So a very nice mathematical example of subconscious bias. Here, even though I had no idea what the scores would be consciously, because I was trying to be unbiased, I've ended up with an equal evaluation of each method. Okay, I'm just going to take another look at things here. Let's see here. Okay, I've changed some of the scores around, and now I actually have something I can select off of. Still a heavily biased thing, because again, I'm just one person. But if I take another look at the wristband design from last week, there's just not a lot of space around the hinge anyway, which is why I increased the score for that this would interfere with the established structure. And so I've ended up with a better method is to simply latch the two ends together. Okay, so the expected score stuff is a pretty interesting method. I'm not sure how much it's helped me here, but I think it helped me choose the end latching method, which is good. Now, before I get to actually designing that end latching method, we need to get to one critical test, which is this pressure vessel actually going to work? Now, I know the aluminum parts are fit for holding the close to 100 psi vapor pressure of the propellant that I'm using, but I'm not sure if all of the seals that I designed last video will hold. I think they will, given I've done the proper calculations and the recommended compressions of O-rings and that sort of thing, but I need to figure that out. Okay, so it was in the last video, I believe I said that the tap that I was previously using for my propellant, which is this thing that you see here, was leaking, and I was wasting a lot of propellant, and I'm not a fan of that at all. So I've bought a new tap, but I'll need to adapt the quick connect, this double shut-off quick connect coupling that I've been using for a long time. I'll need to adapt that to the new tap that I have. Where the heck did I put that thing? Okay, here it is. So I've got this new tap here. This pressure gauge that came with it, I didn't have on my original version. And I'm suspicious that this is actually also a source of leaks. And this pressure gauge wasn't that helpful for me anyway, so I'm just gonna go ahead and get rid of it. Got it. I've got a hose clamp on here, so I'm gonna have to undo that. Just maybe I can yank. Hose barb. So now we take that hose clamp, place it onto the tube. We put the hose barb in. Here we go. We're on nice and snug. Punctured it. And it seems to be sealed because I don't see anything coming out here. And now if we open it up, I think I heard some gas flowing into here. If we press this. get gas coming out. I don't think we have any leaks. So hopefully this works better than what I had before. Yeah, now that we have this, we can go ahead and test the pressure vessel. Plug this in. All right, I think we should be pretty good here. We should have like at least some liquid propellant in here. So it seems like those O-ring calculations we made last time were actually pretty helpful. There was no more trial and error. It was all just mathematical decision making, and we ended up with a really nice valve seal. Check it out. That was good. That was cool. Okay, I'm gonna see if we can get like a really nice high quality close-up of this spraying, maybe even in slow motion. Keep having to stack things on top of here. When will it end? Okay, this is as good as we're gonna get here. So now the question of how to design this end latching system. In all my designs, to keep costs down, I try to keep part count down. That is the number of parts that are in the assembly. One surefire way to keep parts down is to use the same latching method used by common plastic buckles. That is to have a bistable leaf spring inserted into a mating component. Now with this new design, we haven't increased the part count at all. We have the same number of parts as before. Just a simple leaf spring with a tab. Is it the best latching mechanism? I don't know. You guys might be like, why is he spending so much time on this latching system? And look, I get it. It's not the most scientifically interesting part of this project. However, because I'm so interested in making things really easy to use, I wouldn't be against doing a whole video on investigating what the best latching mechanisms are. I just have not had time to do that for this video. I started planning it out a little bit, but it just would have to be its own thing, I think. The question of how to parameterize that is kind of a big one. I don't know if anyone's looked into that before, but I'd be interested in seeing what people have done. For now, we're gonna go with this simple design. So let's move on to the other two features we have to complete. For this part of the video, I've done the redesign off screen, and I'm just gonna highlight the key changes. But first, we get rid of all the parts from the previous version that are going to change, and we bring out the new versions of these parts. All right, I'm in the middle of building this new version. I haven't yet soldered the motor back together, but that will be pretty easy. What I do want to call attention to is, as we talked about, all of these wires that have to pass through the outside of the circuit chamber. And you can see I have everything connected here. So this connection and that connection connected this power button to the battery, and then these two wires here actually connect the battery to the circuit board. So I've come up with this, which essentially matches the profile of the battery itself, because that profile is slightly different from the profile of this circuit chamber. So we add a slight amount of bulk to be able to cover up these wires here. There, that fits quite nicely. Now we just have the power button up here and the battery connection back here. Only external wires are the trigger, and I guess you could say these are external wires. I'm gonna have to solder these motor wires together. So now when we connect the battery, we should be able to see that testing blink sketch that we uploaded to the microcontroller. Okay, battery's connected, and if we turn this on, there it is. So we've solved the problem of having these electronics exposed, but we still need to figure out how to keep this battery on without using the electrical connections as a mechanical joint. Now, to keep the battery in place mechanically, I've actually come up with this super simple solution where I don't have to add any extra parts or moving parts or anything, where the battery, once the bracelet is open, is actually perfectly removable, and all you have to do is put it in when the bracelet is open, and then once you have it in place, you can close the bracelet, and you can see the battery then becomes constrained by this extra part of the ring here, which simply just covers this part of the battery, and now it's in place. So battery can't come out mechanically, and that problem is solved. All right, so I'm gonna try putting this on. Wait, oh. Oops. No, I'm pretty stupid. Okay, give me 1 second. Okay, there, that's much better. Now I can put it on my hand. When it's open, we can attach the battery to the electrical connections. All right, let's see if it's working. Yep. All right, and then we can close it. Boom. Now we're nearly done. Next step is just to program the microcontroller. Okay, I'm gonna be honest, the mechanism for this thing is kind of temperamental. And the issue I've started to realize is this lever here, this long one, it's so long that, you know, what's supposed to happen is this lever pushes down on this tip of this lever. And as a result, this lever rotates around this axis from this screw that you're seeing here. But instead, what's happening is because there's so much leverage, this thing is pushing down here, and it's actually just twisting like this a little bit. So what I've tried to do is, because it can still activate, just push this, you know, basically to the point where the valve is almost being pressed. So this thing is basically loaded, and it's like in quite a bit of, it's like being bent slightly elastically. But if I turn this on now, I don't know if the adjustments that I've made will be enough. The whole device right here, compared to this bulky version just being part of the device before. So definitely a lot smaller. This is battery, microcontroller, pressure vessel, motor, battery. Oh, I already said. Okay, so I've been doing fine tunings on that valve actuation mechanism pretty much all night. But what I can say is I now have a finished design on my wrist. The trigger I didn't really get to today. All I have is my simple FSR, and I just taped it to my hand so it would be easier. But yeah, there it is. So definitely a lot smaller than what we had before. So pretty amazing, because what we had before was extremely bulky, and this has everything that has in a smaller space, which is fantastic, frankly. So we can turn it on. Power button is right here, and here we go. Nice, right? I think it's pretty cool. I also had to recharge the batteries right before this as well, but luckily the battery fits into this over-the-counter lithium polymer cell charger. So it seems like it works pretty well, right? And as promised at the beginning of this video, now that this stage of the project is done, we can get back to dreaming about what's next. For instance, I did have a lot of trouble with the levers in this valve actuation mechanism. And I think I'm gonna have to do something about that, because I don't wanna have to deal with that every time I make a new iteration of this. I really want it to just be more plug and play. Then we have to think about if we can actually miniaturize this thing even further, because this is no piece of jewelry just yet. And then most ambitiously, if you've been watching my videos in the past few months, you'll know I'm working on something called force myography, which is a new way of triggering wearable devices such as these. It replaces this trigger right here, frees up the palm, and it means that eventually this device will just be a self-contained wristband, just everything right here. That's going to be tricky, but I've demonstrated a little bit of my force myography capabilities so far. Next time we are going to go a lot deeper. So to close out this video, I just want to go back to talking briefly about this whole expected score method of design selection. At this point, you might be wondering, is that method even useful? And to be honest, I don't know. It is, however, for sure something you can do to mitigate your decision paralysis if you suffer from that, like I do. This way, whether it's right or wrong, if you have two methods from which to choose that are essentially equivalent, this just makes you go brain off, do math, you pick this one and move on with your day. And it didn't help me with this video that the two designs I was choosing from were rather abstract. So it's no surprise that the probabilities and scores were difficult for me to come up with off the top of my head. Again, typically you'll have a whole group of people sketching out a set of more specific solutions. And then you'll have the same group of people, or I guess even a different group of people could be even better, fill out the table for each solution. So will I use these tools again? I don't know. Maybe I will, maybe I won't. All I know is in 2 weeks, we're gonna dive deeper into the force myography rabbit hole. Next time, we're gonna be collecting data, training neural networks, and testing neural networks. We're gonna enter the land of machine learning. And if you're experienced in machine learning, you're probably more experienced than me, but I will be demonstrating some techniques that I have found to be somewhat unique, and you may learn something anyway. So stay tuned for that, and until then, stay amazing. I'll see you guys in the next one.